Record. Okay, today we will be graphing functions by the characteristics of the first derivative and the second derivative. The first examples, we deal with the first derivative. So first derivatives will give us, once we take the derivative, set it equal to 0 and solve for x, we'll get critical numbers. Well, now these critical numbers will give us the maximum or minimum of a function. So what we're going to do is everything we did last class, take the derivative, solve for x, but now we're going to plant these critical numbers on a number line, and then we're going to find out where the function's increasing, decreasing, and this will give us where our max and minimums exist. But this first page is just all definition. So you have the increasing, decreasing test. If the first derivative is greater than 0 on the interval, then the original function is increasing. So remember that derivative is just a fancy word for slope. So if the derivative is positive, this means that the original's function slope is increasing. And for B, if the derivative is negative, this means that the original function will be decreasing. Because again, it's all about slope. Okay. So with that, we have the first derivative test. This will tell us whether we have a maximum or minimum at a certain critical number. And here is we create a number line, or it's called a sign chart. So number 1 says we have a local minimum if at your critical number, the graph goes from decreasing to increasing. So a local minimum is created. So if we have a graph and it goes from decreasing to increasing, then the point is called a local minimum at our critical number of C. Okay. 2, it says we have a local maximum if the graph goes from increasing to decreasing. So if our graph goes from increasing to decreasing, then we have a local maximum. Okay. And then it says we do not have a local max if our signs do not change. So for number 3, if it says we go from increasing to increasing, then a local maximum, we do not have any local max or local minimums. So increasing to increasing would look like what? I guess like that, right? Increase to increase. So there's no local max or minimum. And then 4 says you don't have a local max or min if you go from decrease to decrease. So I would just reverse that. There's decrease to decrease. No local max or minimum. And that fancy word extremum is just fancy for maximum and minimum. Okay, so this first derivative test, again, what we're going to do is find critical numbers. We're going to put them on a number line and create a sign chart. We're going to see where we're increasing or decreasing. And this will give us a location of maximums and minimums. Okay. So let's go ahead and try it out. Okay, number 1. Find where the function 3x to the 4th minus 4x cubed minus 12x squared plus 5 is increasing and decreasing, and then find the local minimum maximum values. So again, this is everything we did last time. We're going to take the derivative, set it equal to 0, solve for x. The new part is take these x values, put them on a number line, create a sign chart, and this will tell us where we have maxes and mins. Okay. All right, so let's get started. So we'll call step A. We're going to find the derivative. So f prime of x, I get 12x cubed minus 12x squared minus 24x, right? 12x cubed minus 12x squared minus 24x. Good. And then you set it equal to 0. So 12x cubed minus 12x squared minus 24x equal to 0. What could I factor out here?
12x.
12x. That'll leave me with x squared minus x minus 2. And what does x squared minus x minus 2 factor to? That's minus minus. So that's x plus a number, and that's x minus a number. And what are the only factors of 2 that can make -1?
+2 and a -1.
I think it's going to go the other way. Since that middle number is negative, this means that the bigger number has to be negative and the 1 be positive.
Almost there.
Almost. Yeah, you're good. Okay, set each term equal to 0. And what are my critical numbers?
Zero, -1, and 2.
There you go. Here's my critical numbers. Okay. Now we move on to the sign chart. B, I'll say sign chart. Okay. So here's my number line from -infinity to infinity. And we're going to plot these critical numbers on here. Here is -1. Here is 0, and here is 2. And now we have intervals based off the number line above. -infinity to -1, -1 to 0, 0 to 2, and 2 to infinity. Okay. And what we're going to do now is pick test numbers in between each interval and test them into the first derivative. So green, I'll do test numbers, and there's 4 intervals. So this means I'll have 4 test numbers. X equals, X equals, X equals, and X equals. All right. Somebody give me a test number from -infinity to -1.
-2.
-2. Give me a test number from -1 to 0.
-1/2.
Good. -1/2. Give me a number from 0 to 2.
1.
1. And give me a number from 2 to infinity.
3.
3. Okay. So these are test numbers for the sign chart that we're going to plug into the first derivative. So this is a sign chart for the first derivative. So you will plug into f prime of x. So you have f prime of -2, f prime of -0.5, f prime of 1, and f prime of 3. There we go. And now take all of these and plug them into that first derivative above. And you can use your calculator. You can use Desmos. You can make an XY chart. Oh, what was I watching? Hot. Okay. I just hit new, right? New. There we go. Okay. So for Desmos, hang on, let me type in the first derivative. 12x cubed minus 12x squared. Oops. 12x squared minus 24x. And then I'm going to use that table feature, and I'm going to type in these test numbers. All right, -2 is in there for us. Good. -1/2, and then 1 and then 3. Okay. So at -2, I get -96. At -0.5, I get 7.5. At 1, I get -24. And then I get +144. Okay. So back to the notes. All right, let's talk about what we have. So we are testing these numbers into the first derivative to create the rest of the sign chart. The output is going to tell us whether we're increasing or decreasing. So when we plugged in the test number of -2, we see that we got a negative output of -96. What this means is that on the interval, -infinity to -1, no matter what test number you pick, you will always have a negative output. So this means that from -infinity to -1, the function is decreasing. And then we see that when we picked a number between -1 and 0, you got a positive output of 7.5. This again means that whatever number you pick in between -1 and 0, you will always get a positive output. This means that the original function is increasing. And then between 0 and 2, we're negative. So this means we're decreasing. And then from 2 to infinity, we get a positive output, which means we are increasing. Okay. And now our sign chart is complete, which means we can now look for maximums and minimums. So we'll call this C. Max and mins. Okay, so looking at your sign chart, let's look at our first critical number of -1. Look at -1. We are decreasing and then increasing. You are decreasing and then increasing. This means -1 will be a local maximum or minimum.
Minimum.
Good, a local minimum. And then look at our next test number. At 0. At 0, we increase and then we decrease. We increase and then decrease. So 0 will be a local what?
Maximum.
Maximum. And then the very last critical number to look at is 2. At 2, we decrease and then increase. So this means that 2 will also be a what?
Local minimum.
Local minimum. Okay. But now we need to find the exact location of these maximums and minimums. So what we're going to do now is plug these in to the original function. Plug into f of x. So you'll have f of -1, f of 0, and f of 2. And now you have to plug these in to the original function. All right, so I could use Desmos, or actually, maybe not. Let me see, -1, 0, and 2. If you plug -1 in, that becomes +3, that becomes +4, so that's 7. And then that still becomes -12. So 7 minus 12 is -5. So you'll get 0 for the first one. And then 0, that's 0, that's 0, 0, you'll get 5. And then 2, oh boy, that's got some work to do. But 2 to the 4th is 16. 16 times 3 is 48. And then minus 2 cubed is 8. 4 times 8 is 32. So 48 minus 32 minus 12 times 2 squared. That's 4. That's 48. So that's minus 48 plus 5. And you get negative 27. Yay, there you go. And those are the exact locations of your maximums and minimums on the original function. Okay, any questions on that? Dang, everybody left today. Me, Ryan, Amanda, Cole, James, and Sam.
What?
My goodness, look at the list. Look at our roster. Everybody left.
Really?
Yeah.
We're hanging in there till the end.
Any questions on this one?
Have a lot of people dropped?
Nuh-uh. Maybe just it's maybe now they're just watching the videos. They're like, oh, I don't want to hear this guy anymore.
Maybe I should stop.
Feel the
talking so
same
much.
way.
There you go. We all feel the same way. Then I guess we're just gonna have fun then, huh? All right.
Everyone gets an A.
Woo! All right.
Look
So
under
this
your seat.
says, look under your seat, everybody. You get an A. All right. So
Staying here with you, you didn't have anything to do if we all left. When you get extra points, you're like,
whatever. Okay, let's keep moving then. All right. So this one says, find where the function 2 sine of x plus x on the interval 0 to 2 pi is increasing and decreasing, then find the local maximums and minimums. Okay, so same exact as the last one. So this means that A, let's find the derivative. G prime of x equals, and that's going to be 2 cosine x plus 1. Okay. And then set the derivative equal to 0 and 2 cosine of x plus 1 equal to 0. Move the 1 over and then divide by 2. We get cosine of x equals negative 1/2, and they're giving us an interval to work with. They're giving us 0 to 2 pi, which means look at your unit circle and tell me what radian values make cosine negative 1/2. There we go.
2 pi. Oh wait, over 0 to 2 pi. Oh, that's the whole circle. Okay.
Yeah,
You
yeah.
get it. I'm sorry. 4 pi over 3 and 2 pi over 3.
4 pi over 3 and
I went backwards. I don't know why.
oh, okay, and 2 pi over 3. I was like, wait, what's wrong with that?
I want to go clockwise.
There you go. All right. So here's our critical numbers. Okay, which means it's sign chart time. All right, so they're actually giving us intervals to work on this time. So here's 0 and 2 pi. And then here's 2 pi over 3. All right.
I'm really sorry.
You're good. Actually, let me actually make the unit circle so you know what radian values you can pick. So this is 0, and this will be pi over 2. And then this will be pi. And then that'll be 3 pi over 2. And now you know where your values go. 2 pi over 3 is going to be right here. And 4 pi over 3 is going to be right there. Just so you know how to pick your x values. So this means that for my intervals, I have 0 to 2 pi over 3, and then 2 pi over 3 to 4 pi over 3. And then last is 4 pi over 3 to 2 pi. Okay. So now we pick test numbers. And give me a test number from 0 to 2 pi over 3.
Pi over 2.
Pi over 2, look at that. It's already labeled, right? X equals pi over 2. And then give me a test number in between 2 pi over 3 and 4 pi over 3.
Pi.
Pi. And then from 4 pi over 3 to 2 pi, we can use
3 pi over 2.
Woo, there you go. Once again, this is a sign chart for the first derivative. So plug into your first derivative. This one's G though, right? Okay. So f prime of pi over 2, f prime of pi, f prime of 3 pi over 2. Okay. And if you plug those into the derivative, well, first off, cosine at pi over 2 is 0. So this means you'll just get 1. And then cosine at pi is -1. So you'll get -2 plus 1, which gives me -1. And then cosine at 3 pi over 2 again happens to be 0. So you'll end up with 1 again. Yeehaw. And now this is for our sign chart. So it says that any number we pick between 0 and 2 pi over 3, you're always going to get a positive output. This means that you are increasing. And then from 2 pi to 4 pi over 3, you'll always get a negative output, which means you are decreasing. And then, of course, the last is increasing. Now, looking at our sign chart, we can find maxes and mins. And the first one we look at is 2 pi over 3. You increase and then you decrease. What do we have?
A local max.
A local max. And then we look at 4 pi over 3. And we decrease and then we increase, which means we have a local min. Okay, cool. So this means that we want to find their exact location. So we plug them into the original function. So I'd get f of 2 pi over 3 and f of 4 pi over 3. And I'll just use my calculator here. What's the original function? 2 sine x plus x. Also, make sure you're in radians. Let's see. 2 sine x plus x. And I'll type in 2 pi over 3. And I get something funky. Oh, yeah. Okay. Not that funky. I get 3.83. And then 4 pi over 3, I get 2.46. There we go. And these are where your maximums and minimums are located. All right, y'all. Any questions on that page? So just an additional step to what we learned last time. Find the derivative, set it equal to 0, get your critical numbers, plot them in a sign chart, pick test points, find intervals of increase or decrease, which then find your max or mins, which then you plug in to the original function to find their location. All right. All right, cool. Now this one is rational. Ooh. And then after that's concavity. All right. Excellent. So same thing for this one that we did for the others. Find where the function's increasing or decreasing, and then find maximum and minimum values. So A, we want to find the derivative, but it's a quotient. So this means that f will be x, g will be x squared plus 1, f prime is 1, g prime is 2x. All right. This means that f prime of x is going to be f prime g, x squared plus 1 minus g prime f, 2x times x over the denominator squared. And 2x times x we know is x squared. So 2x squared. Okay. And then you get negative x squared plus 1 over x squared plus 1 squared. So there's our derivative. Okay. And then we set it equal to 0. So f prime of x equals 0. And since it's rational, remember that we have two parts. We set the numerator and denominator equal to 0. So negative x squared plus 1 equal to 0. Move that 1 over. X squared equals negative 1. And then divide by negative 1. You get x squared equals 1. And therefore, x equals plus or minus 1 are your first set of critical numbers. And then you set the denominator equal to 0. I don't need that squared in there. I just need that x squared plus 1 equal to 0. You move that 1 over and we stop because you get imaginary or complex numbers. So these are the only critical numbers. Okay. And now we test. Sign chart. Negative infinity, positive infinity. Here's negative 1. There's 1. My intervals. Negative infinity, negative 1. Negative 1 to 1. And 1 to infinity. And then test numbers. X equals negative 2, x equals 0, and x equals 2. Plug them into the first derivative. And let's see. If I plug in negative 2, let's see, that'd be negative 4. It'd still be negative 4 plus 1. So you get negative 3 over 4 plus 1 squared. So -3/25. So this means we are decreasing. And then if I plug in 0, I'll get 1/, hey, I'll get 1/1. So this just gives me a +1. So that means we're increasing. And then if I plug in 2, it's going to be the same result as -2. And there we go. We decrease. Okay. And then 3, local max and mins. So looking at -1, you decrease, you increase, we have a local minimum. X equals 1, increase, decrease, you have a local maximum. And of course, plug into the original function, f of -1, f of 1. And if I plug those into the original function, if I do -1, you get -1/2, so -1/2. And then if I plug it in 1, you get 1/2. So there's where our max and mins are. All right, y'all good with that one?
Yep.
Turbo math. Okay, so that's how you find maximums and minimums. So first derivatives and their critical numbers give you maximums and minimums. The next part of these notes, we're going to get into concavity, which deals with the second derivative. So that's our next page. Here are examples of what being concave up and concave down are. So if we say a graph is concave up, this means you look like this, almost like x squared. And then if you're concave down, well, kind of like -x squared, right? Okay, so these are the characteristics of a graph that could be concave up or concave down. And now the point where concavity changes is called an inflection point. So if concavity changes, then the inflection point becomes an actual point of inflection. So what that means is that once we find the inflection points, they're only possible inflection points. The signs and concavity has to change in order for them to be actual points of inflection. So of course, you'll see what that means once we start working the examples. Okay, so to find concavity, it deals with the second derivative. So by the concavity test below, it says that if the second derivative is positive for all values of x in some interval I, then the graph will be concave upward. So looking at this graph above, this would be concave up, and that would be concave up, and that would be a little bit concave up. And then it says if the second derivative is negative, then your graph will be concave down. Well, this is concave down, that's concave down, and that would be concave down. Okay, so that is concavity. So max and mins come from the first derivative, concavity comes from the second. So let's try it all out. Okay. Oh yeah. And something here, if you absolutely hate making sign charts, we have something called the second derivative test. So the way the second derivative test works is that we'll find the critical numbers from the first derivative. We will then take the second derivative. After we find the second derivative, we're going to take the critical numbers from the first derivative and plug them into the second derivative. And by the second derivative test, if, number one, if the second derivative is positive at our critical number of c, then the graph will have a local minimum. Number two, if the second derivative is negative at our critical number of c, then the graph will have a maximum. And three, if the second derivative is equal to 0 at our critical number of c, then the second derivative test fails and you must create a sign chart. So the second derivative test is nice, but in this process to find concavity, we're still going to have to find a second derivative no matter what. So this can either be a helpful step or it can just be an extra step. So you can decide whether to use it or not. I mean, of course, I'll show how it works, but I think sometimes it's just an extra step. Okay. So example 4, given the function x to the fourth minus 4x cubed, find concavity, point of inflection, max and mins, and use all of this information to sketch the graph. Okay. All right. So first step is to find the domain and the intercepts. All right, how much can I zoom in? Oh, that's probably good. All right. So A, what is the domain of this function given? Or what type of function do we have?
It's negative infinity to positive infinity.
Good, because it's a polynomial. Okay, next is the x-intercepts and y-intercept. So remember, for x-intercepts, you let the function equal 0. So we're going to take x to the fourth minus 4x cubed and set it equal to 0 and solve for x. You factor out an x cubed. That leaves you with x cubed times x minus 4 equal to 0. And our x-intercepts are at 0 and 4. Okay, next is the y-intercept, which is always the easiest. For the y-intercept, you let x equal 0, which means you'll have f of 0. And if you plug 0 into this original function, you'll get 0 minus 0, which gives us 0. So there's where our y-intercept is at, 0, 0. Okay, step A is done. Step B, move on to the first derivative. So we're going to have f prime of x, and the function is x to the fourth minus 4x cubed. So our first derivative is 4x cubed minus 12x squared. Okay. Set the derivative equal to 0, and we'll have 4x cubed minus 12x squared equal to 0. Take out a 4x squared, and that'll leave me with x minus 3 equal to 0. Okay, now set them both equal to 0, and my critical numbers are x equals 0, x equals 3. And now we will create a sign chart. So this is all going to be in step B. There's 0. There's 3. Intervals, negative infinity 0, 0 to 3, and 3 to infinity. Test numbers, 1, 2, and 3. So from negative infinity to 0, we pick negative 1. From 0 to 3, we pick 1, and 3 to infinity, we pick 4. And here you'll get f prime of negative 1, f prime of 1, and f prime of 4. Okay. Now plug those into the first derivative. And if I did so, I'm only going to care about the sign this time. I really don't care about the number. So if I plug in negative 1, that's negative 4 minus negative 12. So we'll get a negative number. And then if I plug in 1, I'll get 4 minus 12, which is still negative. And then if I plug in 4, that's going to be, what is that? 64 times 4. Oh my goodness. So that's going to be a big number. So that's going to be positive. Okay. So this means that we are decreasing, decreasing, and increasing. All right. Perfect. Which means that now on to this step, we look for maxes and minimums. So C. Local max and mins. And we look at our first critical number. We decrease and we decrease, which means the signs do not change. This means that x equals 0 is nothing. It's not a max or a min, which means we go to 3. Or I'll put that here first, right? X equals 0 is neither. Now x equals 3, we decrease and then we increase. So 3 will be a local minimum. Okay. Which means let's find the location of that local minimum. So we plug it into the original function. So that's 3 to the 4th, which is what? 81 minus 4 times 3 cubed. I get negative 27. So here's where our local minimum is. Okay. So the first part's done. That's everything we've been doing today. Now we go to the next part where we need the second derivative. Okay. Did I make this 2 pages? I sure did. Okay. All right. Everybody good so far? Okay.
Doing good.
All right. Okay. So let's get that second derivative. So I'll start on this next page. We'll call this D. F double prime of x. And that's going to be 12x squared minus 24x. 12x squared minus 24x. Okay. And now set this equal to 0. And we get 12x squared minus 24x equal to 0. factor out a 12x, and we get x minus 2 equal to 0. Okay, solve these for x, and we get x equals 0 and x equals 2. These are now called my possible inflection points. Possible inflection points, or my pips. Okay. So what we do next is make another sign chart. Negative infinity to infinity. Plot my possible IPs. And then again, make our intervals. Negative infinity to 0, 0 to 2, and 2 to infinity. And then we pick test numbers. Three intervals, 3 test numbers. X equals, X equals, X equals. And now this is a sign chart for the second derivative. So make sure to plug into the second derivative. Okay, negative infinity 0, negative 1, 0 to 2, 1, 3. And we have f double prime of negative 1, f double prime of 1, and f double prime of 3. Okay, plugging into the second derivative. And once again, I don't care about the number. I just care about the output of the sign. Is it positive or is it negative? And for this one, if I plug in negative 1, that's positive 12 plus 24. So we'll get positive. Then if I plug in 1, that's 12 minus 24. So that's negative. And then if I plug in 3, that's 9 times 12 minus, yep, that's positive. Okay. So here we are positive. Now this time we don't do increase or decrease, right? So this is positive, which means that if you are working with the second derivative and the second derivative is positive, this means that the function will be concave up. And then from 0 to 2, we are negative, which means the function will be concave down. And then last, we are positive, which means we will be concave up. Okay. So there's our sign chart for the second derivative. Now let's take a peek at our possible inflection points. Let's find out if they are actual points of inflection. So we'll call this E. P-O-I, points of inflection. So let's look at our first point. X equals 0. So we see that the sign changes from positive to negative, and we see that the concavity changes from up to down. So since the sign changes and concavity changes, this means X equals 0 is an actual inflection point. Okay, and then let's look at 2. 2, we see the sign changes from negative to positive. And then we see concavity changes from down to up. So since sign change and concavity changes, this means that x equals 2 is also a point of inflection, an actual IP. Okay. So now we need to find the exact location of these IPs. So once again, you plug into the original function. So f of 0 and f of 2. And you just got to remember what that original function was. There you go. So if you plug in 0 to the original function, you'll end up with 0. But then if you plug in 2, you'll get 2 to the 4th, which is 16, and 2 cubed, which is 8 times 4, 32. So you get 16 minus 32, which will give us negative 32. So 0, not negative 32, negative 16. And these are the actual points of inflection. Yeehaw. All right. So now we have all of this information that we're going to use to graph a sketch of this function. But before I continue, any questions?
No.
You guys are good? Okay. So let's look at all the values we have starting back at the first step. My x-intercepts are 0, 4, and my y-intercept is 0. So let me go ahead and plot those, 0 and 4. Woo. 0 and 4. There's my x-intercepts. Okay, and then my max and min, I only have 1. It's at 3 and negative 27. So I'm gonna have to plot that. Let me look at the rest of my y values though. My inflection points are 2 and negative 16. So I have just negative 16 and negative 27. That means I'll go by what, 4s? Sure. Not 4s. Yeah, we can go by 4s. Negative 4, negative 8, negative 12, negative 16, 20, 24, and 28. There we go. Okay. And my minimum, I said, was at 3 and negative 27. So somewhere around here. Here's my minimum. And then my inflection points, which are right here to my left, are at 0, 0 to negative 16. So 0, 0 is already plotted, but now we need 2 and negative 16. There we go. There's my point of inflection. Okay. So everything is plotted. We now will graph the rest of this function by following the sign chart for the second derivative. So looking at that second derivative, it says from negative infinity to 0, we are concave up. So what that's going to look like is I'm going to start at 0 and I'm going to go up. There it is. That's concave up. And then the next part of my sign chart says from 0 to 2, we are concave down. From 0 to 2, we are concave down. Let me zoom in to show you that. So that's just going to curve here and go down. There's concave down. And then the sign chart says from 2 to infinity, we are concave up. So at this point, we change direction. At this point of inflection, we change direction. And we curve back up and out. And all of that was concave up. And there you go, guys. That's sketching a graph by using the local maxes and mins from the first derivative, using the inflection points from the second derivative, and using the concavity sign chart to graph the rest of it. Any questions on that whole process?
Nope.
I'm not even sure.
About what?
If I have questions yet.
Oh, just formulating, right?
Yes.
Okay.
Probably on the whole.
All right. But it gets repetitive because now you're going to find the derivative, first derivative, set it equal to 0, solve for x. Make a sign chart, find your max and mins. And then find your second derivative, set equal to 0, solve for x. That gives you your possible inflection points. Take those, plot them on a sign chart, find where you're concave up, concave down, see if they're actual points of inflection. And if they are, you'll find those points of inflection by plugging them into the original function. And then you'll graph everything. Yeah. All right. Oh, yeah. To show you how the second derivative test works, again, the second derivative test will just avoid a sign chart only on the first derivative. So here we have the second derivative. So if I did a second derivative test, we would take our critical numbers of 0 and 3 and plug them into the second derivative. So f double prime of 0 and f double prime of 3. All right. Well, plugging 0 into the second derivative is going to give me 0, which means that's not good already. It means it fails and you must create a sign chart. Good thing we did, huh? But then if you plug in 3 into the second derivative, 3 gives me, what's that? 12 times 9. I think we did that already. And then, oh yeah. So that'll just give you, let me see. Oh yeah. That's just a negative. Oh, it's positive. Yeah. So that'll be 36. So that means by the second derivative test, if the second derivative is positive at our critical number of 3, this means that the graph will be concave up, which means it will have a local minimum, which then you would plug into the original function to get 3, negative 27. But you see, I think it's just an extra step. So up to you whether you want to use it or not. Any questions on that? All right. Oh yeah, last one. Ooh, yeah. Okay, same thing as the last one. This time with the trig function. given, oh, I still haven't fixed this yet. That needs to be theta. Yeah. All right. Given 2 cosine theta plus cosine squared theta for the interval 0 to 2 pi, find concavity, inflection points, max and minimums. Yeehaw. All right. Perfect. So first step is, of course, find domain and x and y intercepts. Well, here you have cosine and cosine squared. What is the domain of cosine?
Negative infinity to positive infinity.
There you go. And then we want to look for x-intercepts. So we set the original function equal to 0. And you have 2 cosine theta plus cosine squared theta equal to 0. What could you factor out here?
Cosine
Cosine.
theta.
Take out cosine theta. That leaves you with 2 plus cosine theta equal to 0. Okay. Set both of these equal to 0, and you'll get cosine theta equals 0 and cosine theta equals -2. And remember that this is on the interval 0 to 2 pi. Okay. So what values of theta make cosine 0 on the interval 0 to 2 pi?
Pi over 2 and 3 pi over 2.
Good. Are there any values that make cosine -2?
No.
No. Well, that makes sense because the unit circle only has a radius of
One.
1. Good. So we get no values from there. Even if you applied the inverse cosine, it wouldn't work because you'd go out of bounds of -1 and 1. Okay. And now we want that y-intercept. That theta equals 0. So you'd get f of 0 equal to the 2 times cosine 0 plus cosine squared 0. All right. Well, what's cosine at 0?
1.
1. So this will be 2 plus 1, and we'll get 3. So our y-intercept is at 0, 3. All right, cool. All right. Algebra's done. Pre-cal's done, right? Now let's move on to step B. First derivative. All right. So before we do so, let's rewrite this first as 2 cosine theta plus cosine theta squared. And now we're ready to find the derivative. Zoom in, and f prime of theta gives me -2 sine theta plus, what do we have? What is the chain rule derivative for cosine squared?
-2 sine theta cosine theta.
Good. -2 sine theta cosine theta, or cosine theta sine theta, whichever you want. Okay, perfect. Now, set it equal to 0. And negative 2 sine theta minus 2 sine theta cosine theta equal to 0. What could you factor out?
Negative 2 sine theta.
Negative 2 sine theta, you get 1 plus cosine theta equal to 0. Set them both equal to 0. And you'll get sine theta equals 0. And cosine theta equals -1. Okay. And of course, this is still on that interval. Zero to 2 pi. So what radian values make sine 0 on that interval?
Two pi and pi.
One more.
And 0.
0.
There you go. And what values make cosine -1?
Pi.
Pi. Sign chart time. Ooh, all the fun, right? I got a whole page for this, right? Yeah, all right, good. All right, sign chart. We have to work between 0 and 2 pi. So once again, I'll the only one, because everything else is on our unit circle. 0, pi, 2 pi. All right. So here's a critical number. And then pi over 2 is not. So I'll just put that there. But then the rest are pi. And then 3 pi over 2 is not. I made that too long, huh? I can space that out more. Let's see. So there would be pi over 2. And then pi. And then 2 pi. Look at that. Okay. So here are my intervals just based on that restriction. So let me see. We're just going to go from 0 to pi. And then pi to 2 pi. Perfect. Test numbers. 2 intervals, 2 test numbers. And we see them already. So from 0 to pi, we'll pick pi over 2. And from pi to 2 pi, we'll pick 3 pi over 2. And then I'll have f prime of pi over 2 and f prime of 3 pi over 2. Plug those into your first derivative. And sine at pi over 2 is 1. So you get -2 minus 0. So the first one would be negative. And then 3 pi over 2, you get -1. So that'd be +2. And that'd be 2 minus 0. So that'd be plus. Okay. So here we increase, not increase, sorry. Here we decrease and then increase. So it looks like pi is going to be our critical number. The only critical number we can actually use on this closed interval is going to be a local minimum. X equals pi is the local minimum, which means plug it into the original function. So if I plug pi into the original, that'd be -2 plus -1 squared, right? -2 plus 1, so we get -1. Yeah. So here we are at pi and -1. There's my local minimum. Yeehaw. All right. How's everybody doing? All right. Okay, second derivative time. So before I do that, let me rewrite the first derivative down here. So this is for D. F prime of theta is -2 sine theta minus 2 sine theta cosine theta. Okay. And now, before I take the second derivative, I'm going to rewrite this using identities to make our life a little nicer. -2 sine theta, this 2 sine theta cosine theta becomes the double angle formula for sine 2 theta. And that will make the derivative a lot easier because we don't have to use product rule now. Okay, second derivative time. F double prime of theta, I get -2 cosine theta minus, and what is the chain rule derivative for sine 2 theta?
Two cosine 2 theta.
Good. 2 cosine 2 theta. Okay. Now, set it equal to 0. -2 cosine minus 2 cosine 2 theta equal to 0. But we can't move further until we fix this guy. What is a good identity to use for cosine 2 theta? Because we're going to want to, so what we want to do is make this equation all in terms of cosine. So remember that cosine 2 theta has 3 actual identities. So what is a good one to use? That will put this all in terms of cosine.
Two cosine squared theta minus 1.
There you go. 2 cosine squared theta minus 1 equal to 0. All right.
Troy, it was a beautiful big plant, right? You dug it all.
Yes. So -2 cosine theta minus 4 cosine squared theta plus 2. Cool. All right. Doing good, doing good. I guess we could have divided by 2 in the beginning, right? Oh, well. Here. Before we do so, I'm going to rewrite it with highest power first. -4 cosine squared theta minus 2 cosine theta plus 2 equal to 0. And then divide everything by -2. And I should end up with positive 2 cosine squared theta plus cosine theta minus 1 equal to 0. And all we have left to do is factor. So this is an easy one. This will be 2 cosine theta plus a number, maybe. I want to say minus a number. And cosine theta plus a number. Well, what are the only factors of 1?
1.
1, 1, and 1. And now set them equal to 0, and you'll get cosine theta equals 1/2. Cosine theta equals -1. And now this is on the restriction 0 to 2 pi. So what radian values makes cosine a positive 1/2?
Pi over 3 and 5 pi over 3.
Pi over 3 and 5 pi over 3. And which one makes it -1?
Pi.
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 Yep.
Good. These are my possible inflection points. My pips. Oh man, look at that. And now, of course, it's sign chart time. So here's 0. There's 2 pi. And I'll make our actual unit circle again. There's pi over 2. Pi happens to be one of our critical numbers. So I'll put that there. And then here's pi over 2 pi, and there's 3 pi over 2. Okay. So I already plotted pi. Then pi over 3, that's going to go right here. And then 5 pi over 3, that's going to go around here. Okay. Okay. So the intervals I have are going to be from 0 to pi over 3, and then pi over 3 to pi, and then pi to 5, whoops, and then pi to 5 pi over 3, and then 5 pi over 3 to 2 pi. Okay, next is test numbers. Four intervals, 4 test numbers. So 0 to pi over 3. Ooh. How about pi over 4? And then pi over 3 to pi, we can choose pi over 2. And then pi to 5 pi over 3, we can choose 3 pi over 2. And 5 pi over 3 to 2 pi, we can choose 7 pi over 4. And this is going to be plugged into the second derivative. Woo. All right. Plug those into the second derivative. All right. So if you plug in pi over 4 into the second derivative, that means you'll have -2 times the square root of 2 over 2. And then 2 times pi over 4, it's pi over 2. So you're going to get something negative. Perfect. Negative. If you plug in pi over 2, you'll get 0 for the first, and then 2 theta times 2 pi over 2 becomes pi. So you'll get a positive 2. So that'll be positive. And then 3 pi over 2, that is the same result. You get 0 and you get positive 2. And then 7 pi over 4, that's going to be the same result as the first one. So that's going to be negative. Okay. Let me make those look more like plus signs. Okay. So what we're saying is that on the interval 0 to pi over 3, no matter what value you pick, you're always going to be negative, which means that you will be concave down. And then from pi over 3 to pi, you will be positive, which means you'll be concave up. And the same thing here. You will be concave up. And then 5 pi over 3 to 2 pi, you'll be negative, so you'll be concave down. Okay, last step, my goodness. E. You're going to look for inflection points, points of inflection. All right. Look at the first one of pi over 3. We go negative to positive. We go concave down to concave up, which means that x equals pi over 3 is an actual inflection point. And then we look at pi. Here we go from positive to positive. So since we go from concave up to concave up, we go from positive to positive. The sign does not change. This means pi is nothing. Pi is not an IP, which means we just move on. And then we look at 5 pi over 3. Here we go concave up to concave down. We go from positive to negative, which means that 5 pi over 3 is an IP. Almost there. Now we take these values and plug them in to the original function. So f of pi over 3, f of 5 pi over 3, and all the way into the original function. Oh boy, make sure you are in radians. What do we have? 2 cosine x plus cosine x squared. And I'm typing in pi over 3, which is 5/4, Hey, that's nice. And 5 pi over 3, which is also 5/4. Okay, which I mean, we're graphing, so that's 1.25. So pi over 3 and 1.25, 5 pi over 3 and 1.25. All right. My goodness. So let's go ahead and graph this now. So I'm going to make our unit circle from 0 to 2 pi on our axis below. So here's 0. And then here's going to be pi over 2, pi, 3 pi over 2, and 2 pi. Okay. And now let's start at the very beginning, starting with our intercepts. My intercepts are at pi over 2, 3 pi over 2, and 0, 3. So that's what I'll plot here. Pi over 2, 3 pi over 2, and 0, 3. So let's go ahead and do that as 1, 2, 3. Okay. And then let's go look at my local minimum. I didn't get a max, we only got a local min. So we're going to plot the point pi and -1. So here's -1. I could have spaced those out too. Oh, well. All right. So pi and -1 right there. There's my minimum. And then the last thing to plot is our points of inflection. Pi over 3 and 1.25, and then 5 pi over 3 and 1.25. All right. So pi over 3 is going to be right about here. Let's say here's pi over 3. So pi over 3 and 1.25, I'll put right about there. And then 5 pi over 3, I think it's going to be right around there. And we're at the same value. 1.25. Okay. We have everything plotted. Now go ahead and follow our concavity sign chart. From 0 to pi over 3, we are concave down, which right there, maybe like that. And then from pi over 3 to pi, we are concave up. Actually, pi over 3 all the way to 5 pi over 3, we are concave up. And then we're concave down. So let me make this look better. Hang on. Oops. There we go. All right. Zoom in. So it says we are concave down. Right there. And then concave up, 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 right there. And then from there on out, we become concave down. There it is. And voila, guys. That is curve sketching for beginners. Any questions on that whole process?